Welcome to our video. This time we're looking at metal reactivity. It's the first steps video, we'll take you through it. Okay. The simplest kind of reactions we have are between metals and non-metals, and we've had a look at them before. So I might have copper, which is a metal, which is a solid at room temperature. So that's copper metal. And I might react it with a non-metal. I'm going to pick the most dangerous non-metal of the lot, fluorine gas. Just fluorine gas. And I produce, they join together, we call this joining process combination, and I produce something called CuF2, which is copper fluoride, which is a solid. And that is easy to understand. So this whole process, if I was sort of describing it, I'd say this is metal, non-metal. Generally speaking, all metals will react with mostly all non-metals. So this is a kind of common reaction, and we'd expect all metals to be quite reactive to this process. But what's more interesting is when I do a metal with a metal ion when they react together. So a metal cation. So I've already got a metal that's in solution, and I'm reacting it with a metal that's not in solution. So for instance, I might take iron metal that's not in solution, so it looks like basically a black powder, and this time I react it with copper that is in solution. Copper, when it's in solution, looks a beautiful blue colour. So this is copper, this might be copper as part of copper sulfate, for instance. If copper's in copper chloride or copper carbonate, it tends to look a greener colour rather than a bluer colour, but it's basically a blue-green colour. Now what happens when they react together, something interesting happens. Both of them don't really want their electrons. At the moment, copper doesn't have its electrons, which is why it's 2 plus there. So copper's 2 plus because it basically doesn't want its electrons, and it's fairly happy at the moment. But unfortunately, iron acts a bit like a bully boy. So what iron will now do is iron also doesn't want its electrons, but iron, if you like, wants its electrons even less than copper. So iron desperately wants to get rid of its electrons. Copper just gets rid of its electrons. So iron has this desperate need more than copper to not have electrons. So we put iron further up, or more negative, up what we call the electrochemical series, which if you watch the first task video will be explained to you in more detail. So what basically happens is that iron forces copper to take its 2 outer electrons, even though copper doesn't really want them. So what happens there is the iron now goes into solution, which will form a green solution or yellow-green solution, and the copper gets precipitated out as a metal, which it looks like a red metal. So we get iron in solution and copper metal. So depending on where the elements sit on what's called the electrochemical series, again watch the other video for more explanation, you will sometimes get the metals reacting in this way, where even though they both want to lose their electrons, if one has lost them but the other metal wants to lose them more, they flip the electrons around, so that you find that the metal that was in solution will precipitate out, and the metal that was the solid will go into the solution. They will kind of change places, and we call this kind of reaction where they change places like that a single displacement reaction. So we would call the whole thing a single displacement reaction. Okay, that's the first idea. The next idea is another measure of reactivity is what happens when we react a metal with an acid or water. Some metals are so reactive that they will react with water, other ones will need acid to react. And this is reacting with an acid or water. And the general principle is if I've got my periodic table sitting here, so here's my periodic table, I've got column 1 and 2, there's the transition metals and there's a bit on the right hand side, my periodic table. In column 1 and 2, the metals that are sitting at the bottom, so the ones that are sitting over here, generally speaking, are more, these ones at the bottom are more reactive than the ones up the top. And these ones up the top are less reactive. The reason is that the ones at the bottom have their outer electrons are further away from the nucleus. So that's the basic idea of why these ones are. So they're held less tightly, so it's easier, even though all metals want to get rid of their outer electrons, it's easier for the outer electrons from a bigger atom to disappear because they're already quite a long way from the nucleus. So you, for instance, lithium, the top one over here, will react with water a bit, but cesium will react so violently with water, will burst into flame and kind of vaporize and everything, so that there's a definite kind of pattern in it, and that's due to the size of the atom and the fact that its outer electron it's trying to get rid of is well away from the nucleus, so it's easy for it to go. And that makes it very reactive because it's easy for that electron to be taken off the metal atom. Remember, metal atoms always want to lose their outer electrons. The third big idea is to do with corrosion. And corrosion involves a metal reacting with the oxygen in the air to form a metal oxide usually. And in order for this to happen, there's got to be an easy way for the electrons to get exchanged. And one thing that can attract electrons and move them around, even though it won't keep onto the electrons, is water. So water, and particularly water containing lots of ions, like for instance salty water, is a really good medium for this process to happen in. So usually metals will last a lot longer in dry conditions than they will in conditions where there's water, and particularly salty water, where there's lots of ions which enable the electrons to be easily transferred from the metal to oxygen. Of course, any metal, if you heat it up and raise the temperature, almost all metals will react with oxygen in the air. But at room temperature, this salty water helps speed up the process. And in fact, it's acting a bit like a catalyst, which is what you'll learn about next week. So That's the basic process, and corrosion has different names. It's sometimes called rusting, particularly if it's with iron, or with things like copper and brass, which is an alloy, and bronze, which is a similar kind of alloy. It's called tarnishing. So sometimes you'll see these words mentioned, tarnishing, and that happens with copper and copper alloys like basically alloys are mixtures of metals. Alloys, and the two famous alloys of copper are brass and bronze. Probably worth mentioning here that iron and steel is the other one, because steel contains iron. It's an alloy basically. Okay, they're the three ideas for this week.